Hello everyone, welcome to IIT and GATE classes. This is lecture 7 on operating system, and in this lecture we are going to start priority scheduling. So let me solve a direct question on it so that you get more clarity. I have already told you many times that priority scheduling is of two types, preemptive and non-preemptive. So let me show you non-preemptive first and then I will jump to preemptive version. So for non-preemptive, I am making the Gantt chart. Okay, non-preemptive. I have told you many times, once Gantt chart is completed, you may think that almost your task is over. Okay. Yes. So arrival time is 0 for P1. So obviously P1 will be started first since it's non-preemptive. So it will be completed first. Okay. So 0 to 8. P1 is over. So let me cut it down. Now 8 time is over, so we may think that all these processes are available. Okay, at time 0 only one process was available, but since 8 time is there, so obviously all the three processes are there in the system. Now that process will be executed, which is having more priority. Okay, so general scenario you have to remember. General scenario is you can say less number means more priority. It's just like rank. Rank 1 is better or rank 3 is better. Obviously, rank 1 is better. So that is the scenario. Less number means more priority. So priority number 1, you can think like this also. First priority, this is, see this. This is first priority, this is second priority, this is third priority, and so on. So first priority is this now. So obviously P4 will be executed first. P4. So what is the burst time? Only 1. So till 9 it will be completed. Then we will complete P3. So P3 will be burst time is 3, so 12. Okay, P3 is over, then P2 will be completed. Burst time is 6, so it will be completed till 18. Now, since Gantt chart is completed, so now I can answer any question. Okay, like waiting time, okay, or anything like that. Okay, so let me show you waiting time of P2. What is the waiting time of P2? Waiting time is nothing but turnaround time minus burst time. Okay. Waiting time is turnaround time minus burst time. So what is the turnaround time of P2? So turnaround time is process finish time minus process arrival time and then minus burst time. Finish time. What is the finish time of P2? 18. And what is the arrival time of P2? P2 arrived at 1. Okay. And what is the burst time of P2? P2 burst time is 6. So I think you have got it. It comes out to be 11. So waiting time of P2 is 11. You can check it out yourself also. P2 come at 1 and it has started at 12. So obviously 11 unit of time it has to wait. Okay. Similarly, you can calculate turnaround time of, say, let me show you turnaround time of P3. What will be that? Turnaround time is process finish time minus process arrival time. Finish time minus process arrival time. Finish time of P3 is what? Finish time is 12 and arrival time of P3 is 2. So it is 10. And so on. I think you can calculate yourself. Okay. It's really very easy task now. I have showed many examples. You can watch my previous lecture to get more clarity on this. Okay. They can ask average waiting time. They can ask average turnaround time. For average turnaround time, you will sum up all the turnaround time of processes and divide it by number of processes, that is 4. Okay, you will get the answer for average turnaround time and so on. Okay, I should not waste time here. You have got it. So now let me show you the non-preemptive version. Okay, let me jump to the next. So, sorry, preemptive version. Okay, let me jump to the next slide. For preemptive version. For preemptive version. So whatever preemptive version, see, uh, in between we can snatch the CPU. Na? That is the basic meaning. So see this at time 0. Okay, so at time 0, there was only one process, that is P1 in the system. There was only one process. So obviously I have to start it. So I will start it. Okay, so P1 will be started. Now till what time? At till time 1 I will do it. Why? Because at time 1 new process is coming into the picture, that is P2, and its priority is 3. But P1 priority was 4. Okay, so I have to give priority to P2. So obviously P2 will snatch CPU from P1. So now P2 will be executed. P2 will be executed for how much time? Only 1 unit of time. Why? Because at time 2, a new process is coming into the picture. Okay, let me cut it so that you get more clarity. So here remaining time, sorry, burst time na 8. So here remaining time is 7 and burst time is 6. So here remaining time will be 5. Okay, because 1 unit of time I have already executed. So now at time 2, P3 is coming into the picture and P3 priority is 2. So it is having more priority now. So you can check it out like this. At time 2, there are 3 processes in the system, P1, P2, P3. So who is having highest priority? P3 is having highest priority. So it will be executed first. Okay. So P3 will be executed for 1 unit of time. P3 for 1 unit of time. Why 1 unit? Why 1 unit? Because at time 3, new process is coming into the picture. Okay. At time 3, P4 is coming into the picture. So I have to execute it. Okay. So remaining bus time is 2 here. Okay. And P4 will be obviously started at 3 and bus time is only 1. So it will be completed at the same time only. Okay. So let me write it. P4 will be executed till time 4. Okay. And finally P4 is over. So now see this, which is having the highest priority now. So P4 is over. It was priority number 1, so it has been over. And now priority number 2 is the highest here now. So P3 will be executed. Till what time? Burst time is 2. So obviously till 2 time it will be executed. So 6. And then P2 will be executed because next is P2 na. Next priority is P2. So how much time? 5. 5 times. So 6 plus 5, that is 11. And then P1 will be executed. Okay, P1 will be executed how much time? 7 times. So 11 plus 7, 18. Okay, so finally you have got it. Okay, so now see this. This was in non-preemptive version, waiting time of P2 was coming to be 11. See the waiting time of P2 for preemptive version. Okay, so waiting time of P2. Waiting time of P2. So see this. Turnaround time, waiting time is what? Turnaround time minus burst time. Turnaround time is process finish time minus process arrival time minus burst time. Process finish time. P1 is completed at 18. Sorry, P2 na. P2 is completed at 11. Sorry for that. P2 is completed at 11. Arrived at P2 arrived at 1. Okay, and the burst time of P2 is 3. So what is the value? It comes out to be 7. Okay, so waiting time of P2 earlier it was 11, but now it is coming to be 7. And obviously now you may think that a preemptive version is better. Yes, obviously it is better. Why? Because more priority process will be obviously executed first now, so it has to wait less. Okay, so in non-preemptive version, that was the biggest problem. Priority number 4 process. Okay, it was having the least priority, but still it was completely executed first. That was wrong concept. It should not be done. But obviously, it is a type of algorithm, scheduling algorithm. So we have to study it. Okay, and by the way, every operating system has its own requirement. Okay, but if waiting time is concerned and all other parameters are concerned, preemptive will be much better. Okay, because it will give more priority. Na? Real priority algorithm is preemptive only because it will give priority to the process which comes into the picture. By chance, if it is having more priority, okay, then obviously it will be executed first, and more priority means less number. Okay, just like rank 1 is better na, first priority, second, third, and fourth. I think you have got it. I should not waste time here, so please take snapshot of this slide and this slide also. I'm not wasting time on other things like average waiting time, average turnaround time. You can calculate yourself. I have just completed the Gantt chart so that you get more clarity. Okay, I'm jumping to the next slide now. Okay, now. So we may think that, see, this is really very important point. You should remember this properly. Okay. So what is SJF? SJF is nothing but the special case of priority scheduling in which criteria of deciding priority is burst time. Okay, you may argue with me, sir, what is the criteria of choosing the priority? For on what basis I have given this priority? This is priority number 1, 2, 3, and 4, and so on. So the criteria, see, there can be any criteria, but if we take burst time as the criteria, then obviously we will get SJF. Okay, so if it is having the, you can say, a shortest burst time, okay, then it is having highest priority and so on. If that is the scenario, then I will get SGF only. So SGF is nothing but special case of priority scheduling, in which criteria of deciding priority is burst time, or rather I should say non-preemptive case of special case of non-preemptive priority scheduling, because SGF is non-preemptive. If they say SRTF or SRTN, shortest remaining time first or shortest remaining time next, then it is nothing but your preemptive priority scheduling. Okay, I hope I have made the point clear. Please take snapshot. I will jump to the next slide. Okay, so SRTF or SRTN is nothing but special case of preemptive priority scheduling, in which criteria of deciding priority is burst time. Okay, please take snapshot. I'm jumping to next slide. Okay, so next is multi-level queue scheduling. I have written few notes for you. You can copy them all, but let me show you in a freestyle what exactly is multi-level queue scheduling, and then I will read all these points for you. Okay. So what exactly is multi-level queue scheduling? As the name suggests, here we are having multiple queues. Okay. So depending upon the priority of the process, whenever process enters the system, I will check its priority, or there are some certain parameters like if process is having least precedence, if process is having say less, you can say burst time, then it is having more priority. Okay, or if it has been not executed on the system, that then it is having more priority, and so on. So there are many parameters of deciding the priority. Anyway, this is a basic course. I'm not going into that much detail. I'm just telling you that if a new process enters the system, then according to its priority, it will be assigned to one of the queue. Okay, there are multiple queues, and according to the priority, process will be assigned to one of the queue, and there are many parameters of deciding priority. Okay, yes. So and each queue is having its own scheduling algorithm. For example, here we can run RR, here we can run FCFS, here we can run SJF, here we can run SRTF. Okay, and so on. Each queue is having its own scheduling algorithm, and depending upon the priority, process is assigned to one of the queue. Okay, so for example, P1 is having say highest priority, then it will be assigned to the first priority. That means here it will be assigned. Now P2 comes into the picture. P2 is having less priority, it will be assigned to here. P3 is coming into the picture, P3 can be assigned here, and so on. Now P4 is having higher precedence, then it will be assigned here, and so on. Okay, so processes will be executed in the queue one by one, and so on. Okay, so now see this. So this is a actually see this. If this queue becomes empty, only then CPU will execute this process. Okay, when these two queues will be empty, only then CPU will execute this process, these processes in this queue, and so on. So obviously, you can say according to priority, we are executing the processes. And if by chance CPU is executing this process, and why CPU is executing this process? Because both these queues were empty. Now, if by chance any other process enters this queue, then CPU will be preempted from this process and given to this process. I think you have got it. Okay. So hence it is a preemptive scheduling algorithm. Preemptive means because CPU will be snatched from the process and given to the you can say other process. I hope I have made the point clear. Okay, so this is multi-level queue scheduling. I'm not going into details and all. I'm just giving you small idea that how these things are done. Okay, so this is multi-level queue scheduling. As the name suggests, multi-levels. Okay, multiple levels are there. Okay, so real life example can be say you are here. Okay, and there are multiple queues of the person, and you are giving passes, okay, VIP passes to the persons who can watch the show or movie ticket and so on. So now here we can have a line of say VIPs like IAS officers and so on. Okay, and second queue can be for normal upper class persons. Third queue can be for middle class persons. Fourth queue can be for lower class persons. Okay, so I'm just giving you a small idea. Okay, and you are providing the passes. So now when IAS officers are in the queue, obviously you will provide passes to them. Once they are completed, then you will jump to the upper class people. Once they are completed, then you will jump to middle class people. Once they are completed, then you will jump to the lower class persons, and so on. Okay, and actually this example is not so good, but I'm just giving you because this is the harsh reality of India. Okay, so this is the harsh reality that they are partial. Everybody is partial here. Okay, so lower class people, they are not attended properly. Actually, it should not be done, but it is the harsh reality of every country. almost every country. Okay. Yes. So obviously VIPs are given more priority. Na? So that is the scenario. So now imagine you are giving passes to lower a middle class person, and immediately an IAS officer came. So obviously you will stop this queue. You will stop this queue and you will immediately start this. Okay, because IAS officers are coming, so you will give more priority to them and so on like this. I think you have got it. Okay. Now let me read the sentences. Multi-level queue scheduling. As the name suggests, here we have multiple queues. Each queue has its own scheduling algorithm. Processes are assigned to one of the queue based on the priority. Basis of the priority can be memory requirements, size of process, etc. I think you have got it now. Please, I should not waste time here. The things which I have explained here, same to same I have written here. As the name suggests, here we have multiple queues. See this, multiple queues are there. Next, each queue is having its own scheduling algorithm. You can check it out. Round robin, FCFS, SDF, SRTF, and so on. Processes are assigned to one of the queue based on the priority. Okay, based on the priority, I am assigning processes to one of the queue. Okay, now processes can't move from one queue to another. This is a really very important point. Please make some star over it. So once process is assigned to the queue, it cannot be changed. Okay, for example, say P3 process is assigned to this third queue. Okay, so now if I'm thinking that P3 is not getting its turn and all, so what should I say? I will not say that it will be assigned to this queue, or then it can assign to this queue and so on. So it will not change the queue. Processes are not allowed to change their queue. Okay, so for example, real life example can be Chaiwala remains Chaiwala only. He cannot become PM of India. Okay, that is the scenario here, because once you are in this lower class queue, you will always remain in this queue. You cannot change the queue and all. Okay, that is the scenario of your multi-level queue scheduling. Okay, process can't move from one queue to another. Okay, now next is processes in the lower priority queue can be executed only when higher priority queues are empty. I have told you this. When CPU will execute these processes when both these queues are empty. Okay, obviously you will give passes to a lower class or middle class person only when these IAS officers are not coming into the picture. If they are coming, then obviously you cannot attend them. And if you are attending them, CPU will be preempted and given to them. Same scenario. Processes in the lower queue can be executed only when higher priority queues are empty. Okay, if processes of the higher priority enter the system, then process of the lower priority queue is preempted. Okay, I have told you this point also. Hence, it is preemptive scheduling algorithm. I think you have got it. So we call it as a preemptive scheduling algorithm. Please take snapshot. I will jump to the next slide now. Okay, disadvantage is starvation will come. Obviously, na starvation will come when IAS officers are keep on coming and higher class people keep on coming. Then middle class and lower class people will not get their turn and so on. So starvation will come. Obviously, this is the hardcore reality of every country that lower class people will starve. Okay, that is the scenario here. Starvation may come because processes are not allowed to change their queue. If they were allowed to change their queue, then obviously lower class person can become middle class can become upper class can become IAS and so on. So if that was the scenario, then obviously starvation will not come, but here starvation will come. Okay. Yes. So I hope I have made the point clear. Please take snapshot. I will jump to the next slide. Okay, next is multi-level feedback queue scheduling. What is multi-level feedback queue scheduling? So the only difference between the multi-level queue scheduling and multi-level feedback is that here processes are allowed to change their queue. Okay, here the scenario was processes can't move from one queue to another, but in feedback it is allowed. Okay, similar to multi-level queue scheduling, but here processes are allowed to change their queue. Most of the modern operating system uses this scheduling. Okay, so I am just giving you a small hint that how it is implemented and all. Okay, and that's it. Okay, so here also we have multiple queues. Okay, so first of all, process will be assigned to the highest priority queue. Okay, so for example, here I have round robin scheduling. Time quantum is say 2 nanoseconds or 2 units. Just writing 2 units. Okay, so for 2 units, process P1 come into the picture. It will be immediately assigned to the highest priority queue. So for 2 units of time, it will be executed. Now, if still it's not get executed, if it is completed, that's okay. It's completely fine. But if it is not executed, if it is not completed, then it will jump to the next queue. Okay, so here time quantum can be say 5 units of time. So here it will be executed for 5 units of time. If it is not completed, then it will jump to the lower priority queue. Then again, it will jump to the lower priority queue and so on. Okay, so same scenario. When here all processes are empty, then this processes in this queue will be executed. Okay, and when this is empty, then this will be executed and so on. So it's just like that. Now, if process is having very less time quantum or very less burst time, it will be executed immediately. Okay, so that its response time will be minimum. Na? That is the most practical based algorithm. Please try to focus here. When P1 enters the system, it will be executed for 2 units of time. If it is completely executed, then it's over. Otherwise, it will jump to the next queue. And here it will be executed for time quantum 5 units. So if it is not yet executed, it will be jump to the next queue, or you can say if it is completed, then it's okay. Okay, so obviously this is the highest priority queue, this is lower priority, then more lower priority, then more lower priority, and so on. So as soon as process enters the system, it will be given to the highest priority queue, and then it will jump to the lower priority and so on like that. Okay, so now if it is not yet, if it is not executed for a certain amount of time, it can jump to the higher priority queue also. Okay, that is the basic scenario. So most of the operating system uses this scheduling. I've just given you a rough idea, that's it. So this is multi-level feedback queue scheduling. Please take snapshot. I will jump to the next slide. Okay. Yes, I'm jumping now. Okay. So now we are going to start process creation. Now we are going to start process creation. That means how processes are created in the system. So you should remember one basic fact. One basic fact is that in most of the operating system, okay, in most of the operating system, processes are created by existing processes in the system, or you can say new processes. In most of the operating system, new processes are created by existing processes in the system. Okay, so new processes are created by existing processes in the system. Okay, so these existing processes are known as parent processes, and the process which is newly created, that is known as its child process. Okay, the existing processes are parent processes, and the new processes which are created, that are child processes. Okay, so the existing processes are known as parent processes, and newly created processes are called child processes. Okay, so for example, I can say like this: this is a parent processes. Parent process has created 2 child processes, and these child processes have created another child processes, and so on. Okay, so for this child, this is the parent. For this child, this is the parent, and so on. So parent, child, and so on. So we have created a tree of processes. Now, this is known as process hierarchy. Okay, so this is known as process hierarchy. So parent process create child processes, which in turns create other child processes, and so on, forming a tree of processes, which is known as process hierarchy. Okay, I hope I have made the point clear. So what is the common scenario in most of the operating system? New processes are created by existing processes in the system. These existing processes are called parent processes, and newly created processes are called as child processes. Okay, so parent process create child process, parent process create child process, which in turn create other child processes, and so on, forming a tree-like structure, which is known as process hierarchy. Same is the case with our family tree also. No? Your grandparents, and then your parents, and then you, and then your child, and so on. So you say family tree. Okay, that is the scenario here itself. Okay, so your parents are existing, and they are creating you, and you are creating your child, and so on. That is the scenario. Okay, yes. So parent process create child processes. For that's it. Okay, I have explained many times. I have repeated it, so I think you have got it. Okay, so this is known as process hierarchy. Let me write it. This is known as process hierarchy. Okay, yes. Please take snapshot. I will jump to the next slide. Okay, so now few points I have to clear. See, when child process is created, it needs some resources. Okay, when child process is created, when child processes created, it needs resources. What are the resources? Resources like memory, okay, variables, files, etc. Okay, resources like memory, files, variables, etc. It needs everything. Na? Okay. So, what are the common scenarios or what are the basic possibilities? All these questions have been coming GATE, so please try to focus here. When child process is created, it needs resources like memory, files, variables, and so on. Okay. So, what are the basic scenarios? So, first scenario is parents share all its resources with child. Parent share all its resources with child. That means all its memory, files, variables, etc. It will share all of them with its child. Another possibility is parents share subset of its resources with child. Okay, parents share subset. Parents share subsets of its resources with child. Third scenario can be parents share no resource with child. Okay. So, which is the most common scenario? Which you think? By common sense, what do you think? If you think that parents share all its resources with child, that is absolutely wrong. For example, take case of your parent. Parents share all your salary with you. If they share all their salary with you, then obviously you will keep on buying items and all. So at the end of the month, you may not be able to pay rent of your house and your basic necessities also. So obviously, parents will not share all their revenue or all their resources with you. That is not the case. Good case. Okay. Parents share no resources with its child. That is also not good. Okay. For example, if you are not a good child or you have some bad habits and all, obviously in that case only parent will not share your money with you. Otherwise they will share money. So which is the most common scenario? Subset scenario. Okay, so obviously if they are earning say x amount, they will share say 0.1x with you or 0.2x with you and so on, like 10% of their income with you or 20% of their income with you and so on. So that is the most common scenario. So this is used in almost all the operating system, including your Unix and all. Okay, so in most of the operating system, parent shares subsets of its resources with child. Okay, please take snapshot. I will jump to the next slide now. Okay, so now next question comes about the execution part. Execution part. Okay, so what are the possibility? First possibility is both parent and child run parallelly. Both parent and child process run parallelly. Okay. Second is parent wait for child for its termination. Parent wait for child for its parent wait for child termination. Let me write it like this. Parent wait for child termination and then parent resume itself. So parent will go to wait state. Parent will go to wait state. After you can say producing a child, parent go to the wait state, and when child terminate, then parent will resume itself. That is the scenario. Okay. And the third scenario will be child wait for termination. Child wait for parent termination. Child wait for parent termination. And then it resume itself, or you can say child resume itself. Okay, what is the more meaningful thing? First, both see let me show you this third scenario first. Is it meaningful? No, it's not meaningful. So it's just like that you are waiting for your parent, that if your parent is having a shop or a home, then you are not working. Once they will go, you will get uh, you will get uh, you will get your parent shop and home, okay, and then you will start doing your business and all. That is not the good case, nah? Okay, so that is not good. So obviously it is not meaningful in operating systems also. Child wait for parent termination and then it resume itself. It is not the good case. Okay, parent wait for child termination and then parent resume itself. It's somewhat meaningful. Of course, it's not meaningful, not at all meaningful in real life scenarios, but it's meaningful in some cases. I will tell you that also. But both parent and child run parallelly, that is obviously the most meaningful case. Okay, so like you and your parent both are earning at the same time parallelly, and you are helping your parents and so on. Okay, that is the most common scenario. So this is used in most of the operating systems, including Unix. In most of the operating systems, this is the scenario. Both parent and child process run parallelly. That is the basic scenario. Okay. Yes. So, and by the way, I will talk about this scenario after a few slides. Okay. Please take snapshot. I will jump to the next slide. Okay. So next is process address space. I think I have told you many times, process address space. Okay. So I have told you many times that each process has its own process address space. Okay. For example, this is the RAM. This is the RAM, and this part of your of RAM is given to the process P1. Okay, here it will execute and so on. So here itself, it will define all the variables. Okay, stack and so on. Everything will be here itself. So this is the part of the memory which is dedicated to process P1. So now P1 cannot access any other part of the memory because it does not own the memory which it own. It can access, like for example, the land which you own. Okay, on or the land on which you have made your home, that land you can access. Okay, other land you cannot access, na? Because they will ask, uh, they will quarrel with you. Okay, or they will fight with you once you start accessing others land and so on. Okay, so same scenario, every process has its own process address space. Okay, so now what are the scenarios? First is parent. I'm writing in the shortcut manner. Parent and child have same process address space, Second scenario is parent and child have different process address space. Third is parent parent and child share some, or you can say parent share subset of its process address space with child. Okay. What do you think? Which is the most common scenario? So I think you all may be thinking, in according to the real life, this is the most general case that parent shares subset of its process address space with child. But no, actually in operating system it is not the case. Parent and child have different process address space. This is the most common scenario. You can remember like that. See, parent and child, actually they are all processes, na? And each and every process has its own process address space. So obviously child will be having its own process address space. Are you getting it? So each and every process, let me write it, since each and every process has its own process address space, so is the child. That's it. So is the child process. So parent and child does not share any kind of process address space and all. Okay. Yes. Please take snapshot. I will jump to the next slide now. So this is the third case. Okay. So first was uh, resources. Okay. It need resources. It was the first case. Resources. So subset. Parents share subsets of its resources with the child. Second is execution part. So both parent and child run parallelly. Third is the process address space. So they will not share process address space. They will be having different process address space. Now let me show you the fourth parameter. That is the code. Okay. So code means what? Lines of code. Now you have written C program and all, and it will become processed when it's come to the memory and so on. So that is the code. So what are the cases? Okay. First case is code of parent and child is exactly same. Code of parent and child is exactly same. Second scenario can be code of parent and child is completely different. Okay, that means there is no link and all between them. Third is uh, code of parent and child is somewhat same. Okay, somewhat same. Matlab, means it's not like that exactly same or it's not like that exactly different. It is somewhat similar, somewhat same. So what is the most common thing? You may be thinking that somewhat same, na? Like your features are somewhat similar to your parents. You are not exactly carbon copy of your parents. Okay, you are somewhat similar to them, and obviously they are completely different. That is not the case. Okay, you and your parents are not completely different. Okay, some features are matching, and exactly same. That is not the case. Okay, but in operating system scenario, in operating system world, this is the most common scenario. Okay, code of parent and child is exactly same. In real life you may be thinking like that, somewhat same, but in case of operating system, code of parent and child is exactly same. Okay, if you want me to show that why this is meaningful and all, so let me show you here itself. For example, see this is in RAM. Okay, this is the RAM. Okay, and here P1 process is there. P1 process is here. So now P1 process has created its a child process. Okay, so how it will be created? So the simplest case, or what is the simplest, you can say simplest way of creating a child process. Okay, for example, I have something here. Okay, I have something here. What is the simplest case? You just copy it. That's a carbon copy. So you just copy it somewhere else in the main memory, and you will call it as C1. So P1 is the parent and C1 is the child of the parent. And the simplest case will be I will copy each and everything as it is. That is carbon copy. Okay, so child is carbon copy of the parent. Okay, I hope I have made the point clear. So this is the simplest case. That's why it is done in operating system. Okay, so code of parent and child is exactly same. Okay, and see, you can see yourself the process address space is completely different, huh? Because after all they are processes. Okay, so we have just copied here. That's it. Okay, so code of parent and child is exactly same, and this is the simplest scenario. Okay. Yes. So I hope I have made the point clear to everybody. Please take snapshot. I will jump to the next slide now. Okay. So now we will discuss system calls. Okay. So how now question arises how this child process is created and all. Okay. If you want to create a child process, how you can do it and so on. So let me show you 4 system calls related to process creation. Okay. 4 system calls related to process creation. Related to process creation. What are these 4 system calls? So the first system call is fork system call. Many questions have been asked in GATE and other competitive exam from this system call itself. What this is doing? It is used to create the child process. Okay, what fork system call is doing? It is used to create child process. And how child process is created, you can see this. So just copy it. Okay, so whenever P1 will do fork system call, immediately the code of this process will be copied somewhere in the main memory, and we call it as the child process. Okay, and after doing fork system call, both parent and child will run parallelly or concurrently. Okay, so see this, let me write it. It is used to create the child process, and whenever uh, it is used to create child process, and by fork system call and by fork, clone of parent is created. Clone of parent is created somewhere else in the main memory. Somewhere else in the main memory. Somewhere else in the main memory. Okay, and both parent and child will run concurrently. Both parent and child run concurrently. I hope I have made the point clear. Okay, so whenever for system call is done, it is used to create the child process, and by fork system call, clone of the parent is created somewhere else in the main memory. Both parent and child will run concurrently. Okay, yes. So let me jump to the next slide now. So for system call is over. Now let me show you the next system call. We have to do four system calls, na? Four system calls. So now I am going to show you the second system call. That is exit system call. That is, I think slides are getting over. So let me copy the slides. Okay. Yes. So let me jump to the slide. Yes. So for system call is over. Now I am going to do exit system call. Exit system call. What exit system call is doing? It, as the name suggests, it is used to terminate the process. It can be any process. Now, the process which is doing exit system call, it will terminate. Okay, it is used to terminate the process. Terminate the process. Whatever process is doing exit system call, the process will be terminated. Okay. Third is wait system call. Wait system call. What is wait system call? Whenever parent process will do wait system call, then it will go to the wait state till one of its child terminates. Okay, so who can do wait system call? Parent can do the wait system call. Okay, so let me write it so that you do not get confused. Parent can do wait system call, and after you can say wait system call, and it is used to put, and it is used to put parent process in wait state till one of its child, it may have created many child, but till one of its child terminates. Till one of its child terminates. So that is the basic meaning of wait system call. And the last is exec system call. Exec. What exec system call do? Actually, when I will make program, then you will get more clarity. Okay, but let me show you something, or let me show you one line for it. Okay, so whenever, see, first of all, who can do exec system call? Either parent or child. Okay, parent or child can do exec system call, exec, exec. Okay, execute means execute. Parent or child do exec system call. Okay, and as soon as it do exec system call, its process address space will be overwritten by some other process code. Okay, and as soon as its process address space is overwritten by some other process code, so immediately parent child relationship will be broken. Let me show you with a you can say example so that you get more clarity. So parent and child, parent or child can do exec system call. I mean whoever, it's not compulsory that parent should do or child should do. Parent or child, anyone can do exec system call. Okay, and uh, and by doing it, and by you can say by doing exec, uh, its process address space, by doing exec PS process address space is overwritten by some other process code, some other process code. Okay, and parent and child relationship is broken. Parent and child relationship is broken. So it's just like that. Okay, for example, in main memory, here we have parent process P1, and after doing fork system call, P1 has done fork system call, and a new child process has been created, C1. Okay, now if C1 do exec system call, if C1 do exec system call, so now what it will do? So in exec system call, we will supply some address of the code and so on, like that. So that code will come here. Okay, so C1 code was what? Exactly P1 code, same to same copy, carbon copy, because you have done for system call. Now this C1 code will be replaced by this code. Okay, so whatever code you have given in the whatever code address you have given here, so it this code will be replaced by this code. Okay, so now immediately I will say, since I have replaced this code by a new code, so obviously their parent child relationship will be broken na? See what parent demands. Parent demands that their child will do the work according to them now. Like parent is saying you should not go out after 10 p.m. If you are going out after 10 p.m., then your parent will scold you 1 day, 2 day, 3 day. And if you keep on doing like this, you keep on coming late night at home and all, then obviously your parents will say you are not my child now. Okay, I am no longer your father or mother. Okay, you just get out of my house and so on. So same is the scenario here. So parent has created copy, that is child. Now child has overwritten its code by some other code now. So directly indirectly what? Now this child will no longer work according to the parent, because now it will execute another code now. So obviously their parent child relationship will broken. So it's up to you. Parent also can do exec system call, or child also can do exec system call. Whenever any one of them do exec system call, their parent child relationship is broken. That's it. So I hope I have made the point clear to everyone. This is all about the basic introduction to all the 4 system calls. Okay, so that's it. That's all for today. So in the next class, I will show you programs. Okay, how I will show you small C language programs, that how fork system call work, okay, how exit work, how wait, how exec work, and so on. I will show you small syntax and all these kinds of things in the next class itself. Anyway, it's not required, but I will show you small hint so that you get more clarity about all these kinds of things. Okay. Yes, please take snapshot. So I will compile the lecture here itself. Okay. Thank you so much. Bye bye.